Okay, so thank you very much. So this talk will be about the guided quantum walk, so the subtitle of this conference was new algorithms and new platforms, right? So this will mostly be about new algorithms. So it's a new algorithm that interpolates between quantum walk and quantum annealing. And there is a paper on that very recently out already, which contains much more details than I'm talking about. But I'll also talk a little bit about new platforms, talk about yours at the very end, but mostly it's about the algorithm. Okay, so let's take a look at the contents. I'll introduce a little bit of theory about the local amplitude transfer, or the short lab theory, which motivates the guided quantum walk. And then we look at the guided quantum walk from a theoretical perspective. What's the goal and what does it try to achieve? And then we also see how to do it in practice when we don't have all the information about the problem yet. And finally, we'll compare the performance against standard heuristics, which, of course, quantum annealing and the quantum walk, those two between which it interpolates, will be. And we'll also get to QA, and then maybe a little bit less well-known algorithm, approximate quantum annealing, INQA. And then there's a very important thing that I would like to highlight at the end. So all of these are heuristics in which we optimize, classically optimize a few parameters. And if we consider very small problems, it's very easy to overdo the optimization. So we have to take into account properly the cost of the classical optimization in order to send the results without being cheating behind the curtains. Okay, so let's get started. The Hamiltonian of the guided quantum walk is basically a standard quantum annealing or quantum walk Hamiltonian. We have the driver term that induces transitions between the states. It's controlled by a time-dependent hopping rate, which in a quantum annealing interpretation would also encode the annealing schedule, which you would have in front of here and in front of here. And then there's the cost Hamiltonian that encodes the optimization problem that we're trying to solve. And in particular, we'll consider three such problems. One is exact cover problems. They derive from tail assignment, problem in the aircraft industry. Another one is the traveling salesperson problem. And the third one is garden optimization, which is from agriculture and companion planting, where the goal is to arrange plants on a grid such that neighboring plants have optimal symbiotic relations. Okay, so let's look at the theory. The guided quantum walk is motivated by all of these problems that I've just shown. They have a sort of generic energy spectrum of the cost Hamiltonian if we make the problems large enough. And this is important. So we shouldn't only consider very small problems, but if we make them large enough, they are sort of generic and we can treat them in the same way. So let's see how we get to this generic energy spectrum. Here's a picture of all, for a 4-qubit case, for a large one, right? A 4-qubit problem of all the states listed by Hemingway. And this Hamiltonian, the time evolution, induces transitions between states of Hamming distance 1 to first order, right? So this driver Hamiltonian couples all the computational basis states of Hamming distance 1, which means in particular, for instance, it would not couple this one to this one, because the Hamming distance is larger than 1. Okay, so we take this grid of states and we order it by energy with respect to the cost Hamiltonian. So if we order it by energy, we get this picture. Now, for some coincidence, 0, 0 is still the ground state, okay? And then with increasing energy to the right, we have all the other states. It doesn't need to be 0, 0, right? Just in this example. And then the goal is to systematically drive probability amplitude from all the higher energy states towards the ground state. So that's the motivation behind it. And now this is the picture that for very large problems, or larger problems, takes a generic onion kind of shape. So how do we get there? Okay, we increase the size of the problem by 1. This would be a 5-qubit exact cover problem in that sense. It's not the real onion yet. But if we go to 10 qubits, then we see this bulk emerge here. So the states are listed on the y-axis according to their degeneracy. For 15 qubits it looks like this, for 18 qubits it looks like this, and for 21 qubits we obtain this sort of generic onion shape. And in this graph, states are still coupled if they have Hamming distance 1. So we always couple the states which the driver Hamiltonian would cause probability amplitude transfer between. And we call this the hypercube graph. It's not a new thing, and quantum walk was discussed in this context. And then we have a color encoding which shows the Hamming distance towards the ground state. So this is sort of the generic thing for all the kind of optimization problems that I showed in the beginning. So, okay, given this hypercube graph, what does the guided quantum walk now do? So let's look locally at what this Hamiltonian does to only a subset of two computational basis states in this graph. So we take a look at the local Hamiltonian between two basis states J and K with Hamming distance 1. And then the Hamiltonian induces transitions between these states. So the driver Hamiltonian on this subspace will just be sigma x, of course. And the cost Hamiltonian is only the two energies of the states. And then the time evolution under this Hamiltonian is an amplitude transfer between these two states. And this takes the following form. So, and most importantly, so this would be the probability to end up in state J, which can be anywhere in the graph, of course, if they have Hamming distance 1. And it takes a form like this, and crucially, there is one quantity which we call the local energy gap. It's just the energy difference between two connected states. And this is an important quantity because we can plot this hypercube graph in terms of the energy difference between connected states. And then this generic onion takes this shape. So here we plot, so on the x-axis we still have the energy, right? Low energy states here, the ground states here, higher energy states up here. And on the y-axis we plot the largest energy gap, so the largest difference between connected states for every state, right? So for all the states K, we go through the lower energy states J with Hamming distance 1, and the largest of them we plot in this approach. Now, this time evolution here in this two-level subspace are local Rabi oscillations, and we see that they depend the frequency between state J and state K, which are coupled under this Hamiltonian. The frequency depends on the hopping rate, so the prefactor of the driver Hamiltonian, the quantum Walk hopping rate, and this energy difference over 2, and we see that we get an optimal balance of probability amplitude transfer between connected states if they are of the same order. So we want a hopping rate to drive amplitude drive transitions between states on the order of the energy difference between the states over 2. So the constant here is not exactly important, but it has to be on this order to drive systematic probability amplitude. And now the goal of the guided quantum walk, the theoretical picture, is to systematically drive probability amplitude from the highest energy states towards this graph to the ground state. So time evolution will add all the probability amplitude is accumulated in the ground state. This is sort of a semi-classical picture of quantum annealing, of the adiabatic theorem, but it goes beyond the adiabatic theorem in a sense. So let's start this. So the goal is at each point in time to drive systematically probability amplitude towards the ground state. So at the beginning, we would be starting at very strong, very high hopping rates, large hopping rates corresponding to the average energy gaps at large energies. So at intermediate times, we would be driving all the probability amplitude that has accumulated here at medium energies. And at the end of the schedule, we'll be driving probability amplitude, which hopefully has accumulated down here, finally towards the ground state. So that's the idea, that's the hopping rate schedule. We want at each point in time to be the hopping rate given by the average energy gap at a certain energy divided by some constant. So let's see how this looks in practice. We look at a 15-qubit example here. 15 qubits, it doesn't yet display the total generic energy structure, but sort of, right? So again, it's the low energy states of the cost Hamiltonian here and the high energy states here, and on the y-axis the largest energy gap. And then implementing this idea at every point in time would correspond to this gray line, these black arrows here. And the time evolution under this schedule looks like this. So let's first look, so we try different constants here, right? Let's first look at a very small hopping rate. So we take the average energy gap at each point in time over 32, which would be a hopping rate which is very low, which for some coincidence also would come out from a quantum walk. So the optimal quantum walk hopping rate would be somewhere down here. And we see the time evolution under this schedule is an oscillation with very low ground state probability. So what we are doing is we're effectively driving probability amplitude transfer at the low energy states. But we have no chance of accessing all the amplitude that is located at the higher energy states. Only if we make the hopping rate schedule closer to this one theory, then we get a systematic driving of probability amplitude at the high energy states. So ground state probability is still very low. And near the end of the time evolution, we have accumulated all the probability amplitude here, and we drive it towards the ground state, which is why then the curve goes up. So whether the constant is 2 or 4 doesn't really matter. It depends also on the total evolution time. In this example, it's 4. It will be 2 if we make it a bit longer. But that's the principle. That's the theory. All right. So theory tells us choose the hopping rate given by the average energy gaps. Now, how do we do this in practice? Because in practice, we don't know all the energies, right? If we know all the energies, we have the ground state already. So what do we do in practice? And what we do in practice is based again on this observation of the generic energy shape, this onion. So we did this for a lot of these optimization problems, and we looked at the optimal hopping rate schedules that came out, and we saw that these schemes, you can also call it annealing schemes, take a generic shape. And it looks like this. And when we saw this, we thought, oh, this is exactly a typical quantum annealing schedule. So this is in a way I meant that this sort of semi-classical picture motivates why quantum annealing works. It's not exactly a typical quantum annealing schedule, but the deviations from a typical annealing schedule can be modeled very well with Bézier curves. So Bézier curves are these curves where you have some control points which you can draw in a two-dimensional grid, and you can pull them to the right, and you would change the annealing schedule, you would pull it a bit to the right, it's a cubic Bézier curve, you would it would bend dynamically down towards 0. So this is the model, which means we only have to optimize 6 hyperparameters independent of the problem size. So all these annealing schedules, hopping rate schedules are controlled by these 6 hyperparameters, lambda 0 to lambda, it's actually lambda 5. So it's only 6 hyperparameters. Okay, so let's compare the performance now to the quantum walk for the 21 qubit problem. And I've already said the optimal hopping rate for the quantum walk, single hopping rate, would be down here to drive probability amplitude transfers at low energy states. And when we plot it as a function of the total evolution time, we plot the success probability, it looks like this. So at very short evolution times, we see that the quantum walk is better. Why? Of course, because the quantum walk directly drives amplitude transfer at low energy states. And at these short evolution times, the guided quantum walk is still busy accumulating probability amplitude up here. But after some critical evolution times, in fact, the quantum walk takes over. And for very long evolution times, we would go into the quantum annealing regime. That's the reason why we compare to quantum annealing next. So quantum annealing, we look at the time now to achieve 90% success probability. The reason is for quantum annealing, by the adiabatic theorem, we are guaranteed we know that it works in the end if we evolve slowly and long enough. Now we fix the time to achieve, we look at the time to achieve 90% success probability, and then we find, as a function of the number of qubits, so we scale up the problem, but the qubits, we find quantum annealing has this scaling of the evolution time. We also saw this exponent yesterday, actually. And okay, it's exponential, right? Now, if we look at the guided quantum walk, we see a linear scaling in a function of the number of qubits. And this is the point where all the numbers should ring, right? Because how can this scaling be linear if we're solving an incomplete problem, right? So this is the point where we notice that we are sort of cheating. We need to take into account the classical optimization. It's only 6 hyperparameters, right? But still, it's a lot for small problems up to 30 qubits. So how do we do this? How do we account for the cost of the classical optimization properly? And we do this by considering again the time to achieve the given success probability. This is exactly the TTS metric, the time to solution metric. But we modify this, we add to the time to solution now the number of classical optimization steps. Because for each classical optimization, we also have to evaluate the ground state energy. So it's just added on top of that. And if we do this, let's see how it looks like. The ground state probability is a function of classical optimization steps, these 6 hyperparameters, and the evolution time. And we have this 50% line here, and we find an optimal combination of optimization steps and evolution time for a 12-qubit problem down here. Now we did this analysis for all problem sizes, so for the 24-qubit problem, for instance, optimum would be down here. And if we now read off the number of optimization steps and properly take this into account, then we get this picture. So quantum meaning is still the scaling exponent of 0.22, but the guided quantum walk now has recovered the exponential scaling, and it still scales favorably, and most importantly, without cheating. So this is an exponent of 0.12, so it's twice as good. So the point I want to make is it's important to consider the right model to describe the data. And at this point, I want to make a very short digression because it has come up in yesterday's talk too, or in a few talks yesterday, where it's also very important to take the right model to describe our data. And this is the story behind Josephson harmonics. So Josephson junction is, in all this superconducting technology, Josephson junction is the central piece, the central element that we are building. And we as a community have modeled Josephson junctions for 15 to 20 years now, successfully, so far we thought, with a single cosine phi Hamiltonian. But what we noticed when we saw deviations in the Latin Karlsruhe is that this model is actually not a good model to the accuracy that we need in our current superconducting devices. And what we also tested this then in 4 laboratories around the world, and also we analyzed published data from past experiments, and we found that to accurately describe it, we have to include a few percent cosine 2 phi, a few percent, a bit less, EJ3 cosine 3 phi, EJ4 cosine 4 phi, to make the model accurate. So just want to raise awareness of this. This has been actually a very large collaboration. The main coordinator was Johan Kopp, who's also in the audience here today. And yeah, these are the references if you're interested. Okay, so this was the digression about platforms. Let's go back to algorithms and quantum walk. And in the very last slide, I want to talk about the generalization of these schedules from the guided quantum walk. So we're scaling the problem up now, and what we do is the following. We optimize the guided quantum walk schedule, so we optimize these 6 hyperparameters for 30 qubits, and then we use the same hyperparameters up to 40 qubits. So we use the same annealing scheme, or the same hopping rate schedule until 40 qubits. This is a large simulation, it requires thousands of GPUs, but it's just one simulation in a sense, right? Because we don't need to optimize it again. And we compare the results to 2 heuristics. One of them is QA. QA is this heuristic where we start uniform superposition and then apply one after another, alternatingly, the cost and the drive on Hamiltonian with these 3 parameters, gamma and beta, and up to gamma p and beta p. In particular, we consider p equals 6, which means 12 parameters. And on the other extreme, we compare it against INQA, stands for approximate quantum annealing, which needs only a single parameter to optimize, and this is probably a little bit less well known. It's an algorithm that we proposed in 2021, based on the observation that this QAOA scheme implements a trotterization of quantum annealing. We've heard that yesterday, of course, too. And we use a second order trotterization. And then every beta and gamma will be given by these formulas where A of S and B of S are the annealing scheme. And we took the D-wave annealing scheme as an example. But the point is it's called approximate because we optimize tau and we might leave the regime where the trotterization error is small or we describe quantum annealing well enough. But okay, we just optimize the single parameter, see what comes out. So the result is here. Okay, so we optimize only the third qubit problem again, and we apply the same schedule until 40 qubits. We see the ground state probability is increased with QAOA, but the scaling is not. With INQA, which then implements the quantum annealing initialization of QAOA in a sense, we do get a better scaling, but we are still way beyond what we then found the guided quantum walk produces with the same kind of resources, the same sort of optimization steps for this problem, and also the scaling is very much better until 40 qubits. Okay, so we found this surprising. This is why we then published the results, and this I would like to thank you for. This was using the large simulator on the supercomputers. Yeah. This is actually 2000 degree simulation.
So I guess my question has two parts which I'm struggling to unite in my mind. So the essential difference between the quantum walk and quantum annealing is essentially your time independence cost function. Yeah.
So the Hamiltonian is time dependent for all of them. So for quantum annealing, this would be A of S divided by B of S, some annealing schedule. And for the quantum walk, it's a multi-stage quantum walk, if you will, in that sense. So this gamma of T changes over time.
Understood. But there's no time dependence in your quantum walk for the cost function part. Yeah.
No, there's no time dependence.
Yeah. So that's the essential difference, as far as I understand, between the quantum walk and quantum annealing.
Okay. Yeah. If you
next observation is, I guess, the fairer comparison between your value quantum walk and quantum annealing is to have the same number of free parameters. So in the quantum annealing, you just have one, which is your anneal sign. So I guess my question is, have you compared, and can you explain why there might be a difference between that quantum walk with 6 free parameters as what you had, and then some of the ideas that Matthias was talking about with more free parameters in your quantum annealing schedule?
Yes, so when we compare against quantum annealing, so in the results that I showed before, we were using a fixed anneal scheme, and it was based on the observation that guided quantum walk interpolates between the quantum walk and the quantum annealing like evolution. If we make the time evolution long enough, we do get a typical anneal schedule out of the optimization, and then we are in the regime where the adiabatic theorem holds, and where we recover the results from the adiabatic theorem with the quantum annealing behavior. So for long evolution times, the guided quantum walk just reproduces quantum annealing. But we are then interested in the intermediate evolution times, where we're optimizing these specific curves for the hopping rate schedule sort of gives a different sort of a little bit different result.
But by typical quantum annealing, you usually linear amping with both the longitudinal transverse speeds?
No, actually not linear, but a monotonically decreasing function.
Okay.
Typically exponentially decreasing.
Well, I might suggest you try that with non-monotonic schedules, having learned from Matthias' presentation.
Oh yes, and non-monotonic schedules are in principle allowed by the idea. If you pull these Bézier curves up here, you will get like something like this. And if you look at the theoretical example, which might not have been the best example, but here actually also the shape was the shape that came out is a little bit non-monotonic. It sort of goes up and down a bit, and also goes up and down a bit. So yeah, in principle, you should allow for these things.
Practice.
I'm interested in these onion diagrams, and I guess I presume that the one question is how do you know if the problem in hand has this general property? I'm assuming you're doing that because they're small enough that you can handle all the states, but how general do you think that, that observation is that problems have this shape and would work?
Yes, so I introduced those three problems, which I actually presented last year's INQA seminar, and the reason they all have this shape is that they are constructed in a similar way. So we have, like in the travel safety problem, we have some constraints that all of the cities need to be visited, so we have some sum ax minus b squared, and so on. We have the same in the exact cover problem. There we have exactly ax minus b squared, and in this gas optimization problem too, and all the optimization problems under such constraints, they display this generic shape. We do know problems, of course, which do not have this shape. One would be like two-set problems, two-satisfiability, or problems with a large degenerate first decider state maybe. And spin glass problems, for instance, would also have this generic onion shape, but then the bulk would not be as far to the left, but it would be in the middle. But okay, if you cut the onion here, you would also have the bulk in the middle, so also this applies. Yes.
Okay. In the interest of time, let's cut this short. Let's thank the speaker again.